Okay, guys, I'm filming this on a Sunday, so I will try to go over it fast because I have other stuff to do later. This is another one of the most recent papers called Unit 1A. I mean, back in the day, there used to not be a Unit 1A version, so there's a Unit 1A now, 2A, etc. So I keep solving papers, and it feels like I will never solve them all. So it's crazy. But anyway, so this is Unit 1A. Recently, I also uploaded Unit 1 from 2026. This is why I am specifying that this is a different paper. And okay, so without further ado, as they say, let's dive in. So the thing I always say is that you should spend about a minute per mark in each problem. So if a question awards 1 mark, it should take you about a minute. If it awards 10 marks, it should take you about 10 minutes. Okay, let's start. So question 1: which of the following is a scalar quantity? So force, momentum, and velocity are all, of course, vector quantities. So work is a scalar quantity, and we know this because work cannot have a direction, right? It's energy. Okay. Question 2: two forces x and y act at the point. Which of the following vector diagrams shows the magnitude and direction of the resultant of the two forces? Okay. Option A is wrong because to add the vectors in this fashion as they show, you should follow the parallelogram rule, and you add them like that. So that's definitely wrong. And so is B. And then C is promising because we are adding the tail of X to the tip of Y, which is how we add vectors. So in fact, that's the correct answer. And then D could be, I mean, it kind of looks correct, but the direction of the force is totally wrong. So no. So I'm gonna write here that you add the tail of X to the tip of Y. So that's a general rule where you replace X and Y with vectors 1 and 2. Okay, whatever the situation is. By the way, for those of you who are watching these videos for a while now, I played a little bit with the settings in GoodNotes, and I tried to find a setting that would make my handwriting seem less horrible. It still is, but you get the idea. So let me know in the comments if you see any improvement. Okay. Question 3: a copper rod was placed under tensile stress, and the tensile strain in the rod was measured, and we see a stress strain graph. Okay, the graph shows how the tensile stress required to cause a tensile strain in the rod depends upon the tensile strain. Okay, what does point X represent? So option A, the fracture point of the rod. Actually, that's this point over here. Okay. So not that. B, the limit of proportionality for copper. That will be a little bit further down the graph, so somewhere there. So that's the linear part of this graph. I mean, the limit of proportionality is where the linear part ends. So that's definitely not at X. Then X, the maximum tensile strength of the rod. I mean, it says it, I mean, the wording gives away what that point is, and that point is there. I mean, where the maximum tensile strength is. So we are left with D, which in fact is the right answer. Okay, and why is that? X is the yield point, and the yield point is where I'm gonna write it down. Yield point is where, oops, don't have enough space. So let me come up here. It's where the plastic deformation starts. Okay, plastic deformation starts. Okay, and that's the answer. Option 4, a tractor pulls a trailer at distance s in time t. The useful power output of the tractor is P. Which of the following equations gives the force F of the tractor on the trailer. This is one of those situations in which you can find the right answer by dimensional analysis, but let's do it properly first, and then I'm going to show you the trick like I always do. So power is work over time. Work is force times distance S, right, over time. So force is power times time over distance, which is option, let me see, power times time over distance. It's option B, right? For some reason in my notes, I have option C marked. I don't know why I did that. So anyway, let me show you another trick to solve these kinds of problems, which is what I sometimes call the lawyer's way, in the sense that often lawyers arrive at a conclusion by eliminating all wrong conclusions. So in this case, if we multiply, power is joules per second. It has units of watt, which is joules per second. So we have joules per second times seconds, and now I'm examining option A, right? And then distance has units of meters. Okay, so joules times meters is definitely not newtons, so that's wrong. Then B, we prove that it's correct, but let's see what the units tells you. So power is joules per second, right? And then seconds over meters, okay? But joules are newtons times meters, okay? And over meters, we recover newtons, which is the unit we want because we need the force, right? Then option C, you have joules per second times meters over seconds. So you have kind of like energy times acceleration. Okay, so that's definitely not newtons. So that's wrong. And then D, you have distance, which is in meters times seconds over joules per second. So that's totally wrong, okay? So with the process of elimination, you can still find the answer in this case. So look out for this scenario when they show up. It helps you pick up points very easily, okay? 5, a cylinder of aluminium, has a weight of 35 newtons and a volume of 1.32 times 10 to the negative 3 cubic meters. Which of the following calculations gives the density of aluminium in kilograms per cubic meters? Okay, so we know that density is mass per volume, and we know that weight is mass times G, right? So since we are not given the mass, we can use the weight to write the mass as weight per volume times G. So the answer in this case is 35, which is the weight in newtons, over 1.32 times 10 to the negative 3, which is the volume, times 9.81, which is option, which one is it? C. Okay. And again, if you examine all the other answers, they don't make sense dimensionally speaking. So you have to have 35 newtons in the numerator, and so A and B are immediately wrong because the units do not work out. And then D, you have the force in the numerator, so you have newtons, and then the acceleration, meters per second squared, but then you have meters cubed in the denominator, So this doesn't work out either. So again, this problem can also be solved by the process of elimination, okay? So let's go to problem 6 now. An object on the moon falls a vertical distance of 0.32 meters from rest in a time of 0.63 seconds. Which of the following expressions gives the acceleration due to gravity on the moon in meters per second squared? Again, because the moon is in the news, you see how in all the units I have observed that this year they had lots of questions related to the moon. And I guess it's related to the fact that Artemis 2, the mission by NASA, was sent to circle around the moon. And, they tried to build fascination, I guess, in the younger generation. So, which is cool. I mean, I'm not criticizing it. I mean, I think it's cool. So, um, so here we use Suvat equations, right? So I have a video, by the way, on the Suvat equations that nobody ever watches. I don't know why. But in that video, I say that it's important when you are dealing with motion in 2 dimensions to specify which dimension you are dealing with. So here we are dealing with the y dimension, right? Because it's falling down. So in the vertical direction, which is the y direction, we have Sy is equal to uy times t plus 1/2 ay t squared. The initial velocity is 0, right? So that cancels. So we are solving for the acceleration. So ay is 2 times sy over t squared. So it's 2 times, the distance is 0.32. T squared is 0.63 squared. So the only correct answer is C. And in this case, options A and D are immediately wrong, dimensionally speaking. I mean, the units do not work out. But for B, they can work out, but the math is wrong. Okay, so that's also wrong. So, moving on. Question 7, a sphere falls through a viscous liquid as shown. Which of the table describes the upthrust and the viscous drag on the sphere as it accelerates downwards? Okay, so the upthrust, I'm going to draw the vectors actually. So in this scenario, you have the upthrust that points, that points up. Okay, so that's the upthrust. And we have the drag force as well. And we have, of course, the weight that points down. So the upthrust is equal to the density of the liquid times g times the volume. Okay, so it doesn't depend on velocity whatsoever. Excuse me. So it's a constant. Okay, so it's either B or D are the correct answers. Okay, now drag is given by the, let's use green. So drag is given by Stokes force. So it's 6 pi eta, the viscosity, times the radius of the sphere times the velocity of the sphere. So as V increases, because it falls through the liquid, the drag also increases. Okay, so the correct answer in this case is B, right? Yes. So in this case, by the process of elimination, you can only eliminate A and C because the upthrust is constant, right? But then you are left with B and D, and you can eliminate D by realizing that viscous drag depends on velocity, so it cannot be constant, right? So again, the process of elimination works here as well. Okay, question 8. Two arrangements P and Q of identical springs are subjected to the same tensile force F as shown. When one spring is subjected to a tensile force F, the elastic strain energy of the spring is E. Which of the table gives the total elastic strain energy for each arrangement? So, the way to solve this, I'm going to show you 2 ways to solve it. So let's start with the first one. So for one string, we have, spring, for one spring, we have that the energy is 1/2 F times X, okay? And we also have that F is Kx, right? Which means that X is F over K. Okay, let's keep this as a reference, okay, from the information given. And now in series, let me use a clean page. So in series, which is arrangement P, okay, the same force causes a 2x extension, right? So the energy, the new energy, is going to be 2 times 1/2 F times X, or if you will, you can write it as 1/2 F times 2X, because you have one force pulling this way and another force pulling this way. So the total energy is 2 times E, okay? In parallel, okay, in parallel, the force is shared, right, equally over the two springs. So the force is F over 2 on each spring. So the extension will halve. Okay, so in this case, we have 2 times 1/2 F over 2 times x over 2. So the force will be half and the extension will be halved, and we have 2 springs, okay? So these 2 cancels. So in this case, we have 1/2 times E. So that's the energy of the second arrangement, okay? So the correct answer is D, okay? Now another way, I promise I'm going to show you 2 ways. So another way is to do the following. Oops. Even though it's not in your spec, in general it is known that in series, maybe you learned this at your GCSE level. So 1 over k total is 1 over k plus 1 over k. So the total k for the spring is k over 2. So F is now k over 2 times x prime, right? So the extension x prime is 2f over k, which means that we have twice the extension. So the new energy is going to be 1/2 f times 2x, which is 2e. And in parallel, let me underline this and this, so it's easier to see visually. In parallel, the total k is 2k, right? You add them up. So the force will be 2k times x double prime. So the extension is now f over 2k, which is x over 2 compared to the initial one. So the energy double prime is going to be 1/2 f times x over 2, which is 1/2 e. Okay, so again we arrive at the same answer, but notice that there is an easier way as well. I mean, option C. In option C, P and Q store the same energy, so that's immediately wrong. You can eliminate that. And then you can also eliminate B for the same reason, because they cannot have the same energy stored. So the only possible answers are P and Q, but you have to remember that in series, you have a softer system. Therefore, it stores more energy, okay? It's easier to stretch springs in series than stretching springs in parallel, okay? So that's another way to solve it. In either case, you arrive at D, the correct answer, okay? Okay, question 9. A rubber band is initially stretched by an increasing force. When the force is gradually decreased, the rubber band returns to its original length. The force extension graph for the rubber band, is shown. P, Q, and R represent different areas of the graph. Which of the following gives the work done in stretching the rubber band up to its maximum extension? So we're basically dealing with the area under the graph. So this is the situation when we bend, when we stretch the rubber band. So the work done is this area over there, which is nothing else than Q plus R, which is option B. I think there is nothing more to be said here. Okay, so I think let's move on. Oh, there is one more thing to say. In case they asked you to find, let's assume they ask you to find what's the energy spent to stretch the rubber band and then return to its original position. That's pause the video and tell me what you think, or write in the comment, okay? If you found it, the answer is Q in that case, okay? But okay, they didn't ask for that, so let's keep it simple and move on. All right, 10. A person is pushing a trolley at a constant velocity. The floor exerts a force W on the person exerts a force X on the trolley, and the trolley exerts a force Y on the person, and the total drag force on the trolley is Z. Okay, too many forces, let's try to draw them. So, the floor exerts a force W on the person, okay, so that would be this force, okay, so that's W. I guess I should okay, move this vector so it's at the guy's shoes. Okay, so that's W. Then the person exerts a force X on the trolley. Okay, that will be this force. I'm using yellow so it's visible. Okay, X. Then the trolley exerts a force Y on the person. Okay, so actually let's move this where the trolley and the man are touching. Okay, so let's call this force Y. Okay, and the total drag force on the trolley is Z. Okay, so this will be applied on the trolley. Okay, so something like this. This is Z. Okay, which pair of forces is a Newton's third law pair? W and Y. Okay, we have two different types of forces. Okay, so that's wrong by definition. X and Y. Okay, so X, what is X? X is the force exerted on the trolley by the person, and Y is a force on the person by the trolley, right? So let me move this line there. Okay. So that's actually a Newton's third law pair. Okay, why is that? Because you have two different forces. Sorry, forces that have the same type and act in opposite directions in two different objects. Okay, so B is the correct answer. So I'm gonna repeat it here. Newton's third law says that we need to have the same type of force, two different objects, and force is equal and opposite. Equal in magnitude and opposite in direction. Okay, so this was section A, guys. We are ready to move on to section B. Okay, we are ready to start with section B and question 11. I took a short break to sip my coffee and listen to some Lenny Kravitz. By the way, I like music and cinema and all these things, but I still don't know how to incorporate something like that in my channel and in what ways, etc. I'm still thinking about where this channel should go. So, but let's go back to physics. So, question 11, a trolley accelerates from rest at point A down a straight track to point B. The trolley then continues along a horizontal track to point C as shown. The effects of air resistance and friction are negligible, show that the trolley reaches point B with speed of about 3 meters per second. Okay, so let's start a clean page. So for part A, we can simply use conservation of energy. Total energy at A should be equal to the total energy at point B. The total energy at A is mgh, and we take Gp to be 0 at ground level. Okay, so mgh is equal to 1/2 mv squared. I mean, this is a very common equation that appears over and over again. So v is the square root of 2gh, or 2 times 9.81 times 0.5 meters. So v is 3.13 meters per second, which is about 3 meters per second. And I had this wild thought right now. I mean, the brain is a weird kind of thing. I think 313 was the plate number of Donald Duck in the DuckTales. Okay, I'm a little bit older, so the DuckTales was a famous show with Scrooge McDuck and Donald Duck and all those guys back in the 90s. And I believe the plate numbers of Donald Duck's car was 313. Go check it out and let me know in the comments. So anyway, let's move on. Part B. Determine the time taken by the object to move from point A to point C. Okay, so we will do this in, B. We will calculate this in two parts. Okay, so the first part, let's start with part BC, the straight line. So SBC is equal to VBC times TBC. So the time from B to C is S from B to C over V from B to C, which is equal to 1 over 3.13. Again, Donald Duck's number. So 0.32 seconds. Okay. Now for part AB, things are a little bit more complicated. First of all, we have to calculate the length of this triangle. And I'm talking about this triangle, okay? And by length, I mean the length of the hypotenuse, excuse me. So in other words, AB. So let's use Pythagoras. AB squared is equal to 0.5 squared plus 2 squared. So AB is 2.06 meters. Okay. Now SAB is going to be 1/2 u, the initial velocity, plus the final velocity times the time needed. The initial velocity is 0, right? So TAB, and by the way, I went over this a little bit fast, but okay, I should have shown you. Let me go back to the paper. Let's find the formulas. Okay, so the Suvat equations are over here. Okay, let me box them. So basically, you have to look out for an equation that includes distance, velocity, and time. It doesn't include acceleration in this case. Okay, so the only option is the first equation, this one. Okay, because even though we do know the acceleration, it's on an incline ramp and it creates also all sorts of problems. So it's easier to use the first equation. Okay, let's go back. So TAB is 2SAB. And by the way, I call this AB, but it's really SAB. Okay, it's the same thing. Over V, the final velocity. Okay, so TAB is 2 times 2.06 over 3.13. Again, Donald Duck's car. So 1.32 seconds. So T total, I'm going to write it down here, squeeze it there. So 0.32 plus 1.32 yields 1.34 seconds. 1.64, excuse me. 1.64 seconds. Let me box it in red. Okay, there. All right. So this was problem 11. I think straightforward. Let's move on to question number 12. So there it is. Okay, question 12. A student carried out an experiment to determine the Young modulus of constantan. Okay, it's a material. The student had a constantan wire with cross-sectional area A of 3.97 times 10 to the negative 7 meters squared. The unstretched length X of the wire was 4 meters. A, the student had enough slotted masses to apply a weight up to 150 newtons to the wire. The breaking stress for the constantan is about 420 megapascals. Deduce whether the wire could support a weight of 150 newtons. Okay. Let's start with that and then come back for part B. We need a clean page. By the way, with these units that are called Unit 1A, Unit 2A, They don't really give you space to work out the problems. But if you scroll back to the back of the paper, they give you space, for example, over here. I don't know why that is, but we will work with clean pages as I do. Okay. So, all right. Question A. The weight is 150 newtons, and the braking stress, let's call it sigma BR, okay, is 420 megapascals. Okay, so let's find how much weight we need to break the wire. Okay, so sigma break is going to be equal to the weight that it's going to break this wire over its cross-sectional area. So W break, which is the weight, is A times sigma BR. So 420 times 10 to the 6 megapascals, pascals, and a pascal is a Newton per square meter. And then the cross-sectional area is 3.97 times 10 to the negative 4 square meters, which I take from here. Okay. So meters cancel. For those of you who are watching this video for the first time and they haven't watched material from me, I usually try to arrive at the final algebraic expression, and then I plug in numbers once I am done with the algebraic expression, and I put all the numbers to the left, so numbers, and all the units to the right. Okay, I hope this makes sense. If you work this out, you will find 166.74 newtons, which is larger than 150 newtons. So yes, it can support 150 newtons. Okay, it will be fine. Part B. The student added slotted masses to the wire and determined the corresponding extensions. The student plotted a graph of force against extension as shown. Show that the stiffness of the wire is about 1.3 times 10 to the 4 newtons per meter. Okay, so recall that F is K times delta X, which of course has the form Y equals to M times X plus C, but C is 0 because it passes through the origin of the axis. So the gradient of this curve is going to be K pretty much, okay? So you can use, first of all, you need to use the straight part of the graph. So this part is kind of straight. This part is, okay, so up to that point there, the graph is straight, okay? So again, you can use any 2 points. Which one did I use? I used exactly that actually, okay? So that. So you can use that and the origin, okay, to calculate the gradient. So this is delta F, which is equal to 60 newtons. And this is delta X, which from the graph, you can figure out that it's 4.6 millimeters. Okay, I don't know why the screen does that weird effect sometimes. Perhaps I'm gonna edit it out, we'll see. So let's go back here, so we have space to work, do part B. So the gradient is equal to delta F over delta X, or 6 newtons over 4.6 millimeters. So 60 over 4.6 times 10 to the negative 3 newtons per meter. So this is equal to 13,043. So 13,043.5 newtons per meter, which is about 1.3 times 10 to the 4 newtons per meter. Okay, and this was K. And this was part 1. Okay, we found the stiffness. We now need to solve for part 2. The relationship between the stiffness K of the wire and the Young modulus E is given by K equals to E times the cross-sectional area over X, where x is the unstretched length of the wire and a is the cross-sectional area of the wire. Determine a value for the Young modulus of constantan using the student's data. Okay, we found the stiffness, so we can just plug numbers in. So let's first solve for the Young modulus. This is going to be k times the length over k over the cross-sectional area, excuse me. So k was calculated to be 13,043.5 times the length, which is 4 meters, over 3.97 times 10 to the negative 7, and then my units are over here. So for the length, we have meters. For the k, we have newtons per meter, and then meters squared. So we get units of Pascal, as we should, and the result is 1.31 times 10 to the 11 pascals. Okay, done. Question 12 is done. Let's move on to the next question. Question 13. A coat hook is attached to a smooth door by a screw as shown. The diagram below shows 3 of the forces that act on the coat hook when a coat is hung from it. The weight of the coat hook may be neglected. Okay. Add a labeled arrow to the diagram in the answer book to show the additional force required for the coat hook to be in equilibrium. Okay, so the moments balance, the weight is balanced by the vertical force from the screw, but we have this force, let's use red, that is not balanced by anything, okay? So it needs to be balanced by this force, okay, which is the reaction force from the door, okay? Yeah, that's the force. So let's move on to part B. If too many coats are hung on the coat hook, the hook will rotate and pull the screw out of the door. Point P is the position of the pivot as shown. The maximum horizontal force from the screw is 150 newtons. The mass of one coat is 2.6 kilograms. Deduce whether a person could hang more than 2 of these coats from the hook. Okay, let's balance the moments around P. So let's take moments about P. This is P. So the weight of the coat times the distance from P, which is 2.5 centimeters, is equal to 150 newtons times the distance from P, which is 0.9 centimeters. So centimeters cancel. So the weight ends up being 54 newtons. Okay, so so that's the weight we can support. So one coat has mass of 2.6 kilograms. Thus, the weight is equal to 2.6 times 9.81. So that's 25.5 newtons times weight. That's, sorry, I don't know why I got confused. Okay, so I'm trying to say that the weight of one coat is 25.5 newtons, okay? So 2 coats weigh 51 newtons. Thus, only 2 coats can be supported, okay? Because it doesn't make sense to say that 51 newtons is less than 54 newtons. Therefore, we can hang 2.3 coats. There is no such thing as 0.3 of a coat, okay? So 3 coats would weigh, in this case, 76.5 newtons. So I'm going to write down 3 coats would be 76.5 newtons, which is larger than 51 newtons. So, no. Okay, and this was question 13. Okay, kind of straightforward. So, let's move on to question 14. Okay, question 14. A small sphere is moving horizontally through a viscous liquid. Question A, Stokes' law can be used to calculate the drag force on an object. State the conditions that must apply for Stokes' law to be valid. Let's use a clean page. So we need laminar flow. That's the first condition. We also need, why did I write an equal sign? We also need spherical objects. Okay. And we also need low speeds. Okay, that's this question A. Part B, there is a constant force of 2.3 times 10 to the negative 5 newtons acting horizontally on the sphere in the same direction that the sphere is moving. The diameter of the sphere is 4.5 times 10 to the negative 3 meters. The viscosity of fluid is 7.1 times 10 to the negative 2 pascals times seconds. At one instant, the speed of the sphere is 5.2 times 10 to the negative 3 meters per second. Calculate the resultant horizontal force on the sphere. So let's do B, then part I. So so we are given again. So let me write. Let me copy down. So the force is 2.3 times 10 to the negative 5 newtons. The diameter of the sphere is 4.5 times 10 to the negative 3 meters. The viscosity is 7.1 times 10 to the negative 2 pascals times seconds. And we are told that at one instant the velocity v is 5.2 times 10 to the negative 3 meters per second. Okay, so the Stokes force tells us that Fs is equal to 6 pi times the viscosity. Wait, what are we trying to calculate? The resultant force. Okay, so first of all, we need to find the drag force, okay? Because as the sphere moves, there is this force, F, that pulls it forward, and then there is the drag force, which is Fs, pulling it back. This is what we are trying to calculate, okay? So 6 pi times the viscosity times the radius times velocity. So 6 pi times 7.1 times 10 to the negative 2 times 2.25 times 10 to the negative 3 times 5.2 times 10 to the negative 3. Okay, so the units are, for eta we have pascals, which is newtons per meter squared, times seconds. Then we have meters per second from the velocity, and then again meters from the diameter. So meters cancel, meters squares cancel, and the seconds cancel, and we are left with 1.57 times 10 to the negative 5 newtons. Now sigma F is simply F minus Fs, and we take the positive direction to be the direction of motion. Okay, so 2.3 times 10 to the negative 5 minus 1.57 times 10 to the negative 5 yields 7.3 times 10 to the negative 6 newtons. Okay, part 2, calculate the maximum speed of the sphere in the horizontal direction. Okay, this takes a little bit of thinking, but the idea is that the maximum speed is the terminal velocity, which is going to be reached when sigma f is 0. In other words, this is going to be reached when the Stokes force equals this force F, okay, which I boxed here in red. Okay, if this doesn't make sense, ask me in the comment section and I'm going to reply. So let's write it down. The speed will keep increasing, okay? Will keep increasing, okay, until the Stokes force is equal to the force, in which case the ball, will reach terminal velocity. Okay, That's the idea. Okay, so we're gonna write down that we need 6 pi. In other words, okay, Fs must be equal to F. So 6 pi eta R and then V terminal is going to be equal to F. So the terminal velocity is going to be F over 6 pi eta R. So that's 2.3 times 10 to the negative 5 over 6 pi times 7.1 times 10 to the negative 2 times 2.25 times 10 to the negative 3. And the units are the forces in newtons. Then we have eta in the denominator, so that's newtons, meter squared, and then seconds. And then R is in meters, so newtons cancel, we have the meters cancelling, and we uncover meters per second, which is velocity. So the terminal velocity is 7.64 times 10 to the negative 3 meters per second. Okay, so that's the final terminal velocity. Okay, long problem, but again, I think straightforward. Let's move on to question 15. Okay, 15, it's a long writing problem, and I frequently say that in writing problems, if the problem awards 6 marks, you should provide about 6 proving points, 6 sentences, something like that, okay? So let's read the problem. A Galilean thermometer consists of closed glass cylinder. Let's go again. A Galilean thermometer consists of a closed glass cylinder containing a liquid. In the liquid, there are several identical sealed glass bulbs as shown. Attached to each bulb is a metal disc labeled with a temperature. Each disc has a different mass. Okay, that's the key there. So identical bulbs, but the metal discs have different weights. Okay. As the temperature increases, the density of the liquid decreases. This can cause the bulbs to move within the liquid. Explain why a particular bulb will float until the temperature of the liquid exceeds a certain value. Okay, so let's use a clean page. So basically, okay, this question 15. So the upthrust is equal to the weight of displaced liquid. Okay, let's begin with that. So all bulbs have the same size. Okay, the same size. So the same volume is displaced and displaced, which is equal to, okay, upthrust is rho GV. So U, the upthrust, only depends on the density of the liquid. Okay. If the upthrust is larger than or equal to the weight of the bulb, and remember there is a disc plus disc, okay. Why did I cram everything there? Of the bulb, okay, plus disc, okay, the bulb floats. As the temperature increases, the density of the fluid decreases, so the upthrust decreases. Okay, so at a specific temperature, the upthrust becomes smaller than the weight. Okay, so the sum of all forces accelerates the bulb towards the bottom. So it sinks. Okay. Now each disc has a different mass. Okay. So a different weight. So the bulbs, excuse me, sink at different temperatures. So to sum it up, the upthrust is proportional to the density of the liquid, right? All bulbs have the same volume, therefore the upthrust is the same for all of them, but they have a different weight hanging from them, okay? So depending on the density of the liquid, the upthrust will lift different bulbs that show different temperatures, okay? So that way you can measure the temperature pretty much. I hope this makes sense. If it doesn't, ask me in the comment section and I'm gonna reply. Okay, this was question 15. Okay, question 16. The toy aeroplane in the diagram has a spring mechanism connected to the wheels. When the aeroplane is pulled backwards, the wheels rotate backwards and the spring is compressed. When the aeroplane is released, the force from the spring propels the aeroplane forwards. The aeroplane is pulled backwards and released from rest. The aeroplane then moves forward in a straight line along a flat surface. The simplified acceleration time graph for the forward motion of the aeroplane is shown. Okay. By the way, I never really liked these toys when I was a kid. I don't know why. They always looked cheap to me. I didn't like them. So I always liked delegate toys, like things that had, I don't know, electricity, batteries, a small motor, something like that. Okay. Yeah, the question A is down here. Okay, sorry, I got distracted. Show that the maximum velocity of the aeroplane is about 3 meters per second. So this is a nice occasion in which you can use the area under the curve because you are given the acceleration time curve, okay? So what do we get if we multiply? So, okay, I'm talking about this area over here. So the area under the curve is the velocity we are looking to find. So what's the area? We have 2 is the acceleration. And what kind of units is that? Meters per second squared. Times, what's the time? 1.6 seconds. So seconds cancel. So we find 3.2 meters per second. You can also use Suvat equations with the time that is shown in the graph and the acceleration from the graph, but I think this is a more elegant solution because you use the area under the graph, which is cool. Okay. Part B is over here. On the axis in the answer book, draw the corresponding velocity time graph for the aeroplane. And now we do have to go to the back of the paper and find the graph. So here is the graph. Okay, let's close this. And we need to do some calculations first. I'm going to do them right here. So I think this is going to be confusing. Let me copy the graph. I think this is going to be easy. Air. So let's copy this graph. This is the select tool. So let's try to copy. Oops, we don't need that. So let's copy this graph. Okay, this is what we need. This part and then this part. Okay, cool. Let's do copy. I hope this works. I just want you to have a picture of what's going on. Let's see. Paste. It only copied, well, I didn't copy the part I wanted. I don't know why. Let's go back again. I'm sorry about that and for wasting your time. Let's, okay, let's try one more time. So, I think I know what I did wrong. Okay, this is embarrassing, guys. I'm sorry. I have to screenshot this part, okay? So that's the trick. That's the tool. Okay, and then we need to do copy. Okay, great. I think this is gonna work. And let's go back and find the empty graph paper. And now, let me see. Yes, okay. So that's the graph. Okay. I put it there so you see what's going on. So first of all, we need to calculate a few things. So first of all, from 0 to 1.6 seconds, so up to here, which is the first part of the graph, okay, we have v is equal to the initial velocity times t plus a times t. So the initial velocity is 0. So the final velocity is 3.2 meters per second, which is also something we calculated earlier. So that was an overkey. But anyway, from 0 to, sorry, from 1.6, oops. Okay, there. Let's erase this. Now, from 1.6 to 3 seconds, which is this part over there, the acceleration is 0, so the velocity is constant, equal to 3.2 meters per second, right? I mean, nothing changes. Okay, and from 3 to 7 seconds, so this part, we can calculate the velocity v starting using the same equation as before. We have, by the way, why did I write u times t here? I'm sorry about that. That's simply u. I'm sorry. Okay, so that's 0. Okay, so from 3 to 7, we have the velocity, the final velocity equal to the initial velocity, which is 3.2, right? Minus at. Okay, so 3.2, and then minus the expression is 0.8, minus 0.8, right? Because it's negative, it's a deceleration, times 4 seconds. So that's actually 0. The final velocity is 0. Okay, so let's draw all these things. So let's call this this velocity. Okay, let's put 3.2 is meters per second is the velocity on the y-axis. That's the only velocity we need, but the previous one will be, of course, 1.6. I mean, in terms of the squares. So anyway, so 1.6 is this point over here. So from 0 to 1.6, we have acceleration. And then from 1.6 seconds to 3 seconds, we have motion with constant velocity. And then from 1.6 to 7 seconds, we have deceleration. I need a straight curve. I'm sorry. Okay, straight line. Okay. Yeah, that's the graph, guys. Okay. I hope this makes sense. Okay. This was part B. And then part C, I wonder if it's here. The wording is not here, so we have to go back to find what the part C is asking. I'm sorry about that. So part C of this question is this one. Calculate the total distance traveled by the aeroplane after the release, okay? For this, we can use the graph we just drew. Okay, let's go find it again. I'm sorry for this confusion. So this area, okay, because it's a velocity time graph, the area under the curve is the total distance traveled. So we're gonna solve this problem here. So S is the area under the curve. Okay, so this is a trapezium, and the area of a trapezium is 1/2 times base 1, which is 7 seconds, plus base 2, which is 1.4 seconds, this part over here, times the height, which is 3.2, yields 13.44 meters. This was a nice problem, I believe, and this was question number 16. Let's move on. Okay, question 17. The diagram shows two bumper cars, P and Q, at an amusement park. Q was stationary, P was moving at a speed of 2.1 meters per second towards Q. P collided with Q. After the collision, P and Q moved off in the same direction. P moved with a speed of 1.15 meters per second. Q moved with a speed of 1.57 meters per second. Show that the total mass of Q was about 150 kilograms, and they give you the total mass of P as 250 kilograms. Okay, let's create a clean page. So this is 17. We are told that the initial velocity of P is 2.1 meters per second, which I write as UP. The final speed of P is 1.15 meters per second, and the final speed of Q is 1.57 meters per second. So part A, we simply need to use the conservation of linear momentum. Linear because it's one dimension, okay? The two-dimensional part comes in unit 4, okay? So the mass of P times the initial velocity of P, which is the situation before, is equal to the situation after, which is to the momentum after the collision, in other words. So mass of P times the final velocity of P plus mass of Q times the final velocity of Q. So mass of Q is equal to the mass of P times the initial speed of P minus the final speed of P over the final speed of Q. All right, so 250 times 0.95 over 1.57 yields 151.3 kilograms, which is about 150 kilograms as asked. Part 2. State one assumption you made in your calculation in A, part 1. So no horizontal forces during the collision. So no external, okay, it's important to write external, okay? External horizontal forces during the collision. Okay. Part 3, the collision lasted a total time of 1.35 seconds. Calculate the average horizontal force on Q during the collision. Okay, so this is an internal force, okay, when we are dealing with momentum. So Newton's third law is related to momentum in that when two objects collide, let me show you down here. Okay, so at the moment of the collision, so let's say we have two objects A and B, okay? So object A exerts a force Fa on object B, and object B exerts the same force in the opposite direction on A, okay? So Fa and Fb are equal to each other because this is a Newton's third law pair in collisions, okay? That's why momentum is conserved. All right, but here they ask us to calculate, let me see, on Q, so they ask us to calculate this force. Actually, I don't know why I wrote A and B. It would be better if I wrote, I mean, let's work with the situation we have. So this is P and Q. So we are asked for Fp, and this Fq, okay? And Fp is equal to Fq. All right, so let's do part 3. F is equal to the change in momentum over time, okay? And the change in momentum is equal to the mass of Q times the change in velocity of Q over delta T. So we have 151.3 times the change in in velocity of Q is just 1.57 because it starts from rest, right? 1.57. And then the time for the collision was, as we were told, 1.35. So this is 175, excuse me, 0.9 newtons. And we are still left with part B, Explain why P decelerates during the collision. Your answer should make reference to Newton's laws of motion. Okay, we need another clean page. So this is part B. So P exerts a force on Q. A force on Q. So due to Newton's second law, Q accelerates. Okay. And it accelerates because a force is exerted on it, right? I mean, it was sitting there without moving, and then a force was exerted to it, so it starts accelerating. Okay. By Newton's third law, okay, Q exerts an equal in magnitude, okay, and opposite in direction force. Okay, so this force opposes P's motion. Okay, P's motion. So P decelerates. Okay, so this is a proper answer, I believe. So this was question 17. Let's move on to question 18. Okay, a stunned motorcyclist wants to jump across a river to land on the other side. The diagram shows the motorcyclist driving off a ramp at the edge of a river. So the ramp is at an angle of 25 degrees to the horizontal, and the height of the end of the ramp is 3 meters. The width of the river is 100 meters. The initial velocity of the motorcyclist is 35 meters per second. Question A, calculate the horizontal and vertical components of the motorcycle's initial velocity as it leaves the ramp. Okay, so you have to analyze the velocity vector. So this angle is 25. So I don't know why I cramp things like that. Okay, so this is the horizontal component. So U horizontal, this is 25. So this is equal to U, so 35 times the cosine of 25. Again, when I calculate components, when a component touches physically, so in this case, the component does touch the angle of 25, that's a cosine, okay? So this is 31.72 meters per second. And then the vertical component, I'm going to write it up here, U vertical is 35 sine 25, excuse me, 25. So this yields 13.8 meters, actually 13.79 meters per second. Okay, part B, deduce whether the rider lands on the other side of the river, the effects of air resistance can be ignored. Okay, let's create a clean page, and this is part B. So, okay, it's a little bit of a weird problem in that we have a ramp, okay. So let's draw the ramp over here. So that's 25 degrees. And this height is 3 meters, okay. So the cyclist will fly off, but then it's gonna land 3 meters down, okay. It reminds me of the rock group 3 Doors Down, by the way. Okay, they have a really nice song about Superman. I mean, go look them up. It's a nice group. So, all right, let's write what's going on here. So the bike needs to fly all the way to minus 3 meters. Why minus? Because this is the zero of the y-axis, okay? I mean, it starts from here. So if it lands over there, it will be 0 meters. But now in this case, we fly all the way down to minus 3, right? Because he needs to travel down the ramp on the other side of the river, which is over there. Okay, so we will use the Suvat equation as V for vertical is equal to U vertical times T plus 1/2 the acceleration in the vertical direction times T squared. So SV, in this case, is going to be -3, and this is equal to the initial velocity, which is 13 point, let's call it 8, T minus 9.81, which is of course the acceleration due to gravity over 2, T squared. So we get this quadratic equation, okay? So 4.91 T squared minus 14.8 T minus 3 is equal to 0. So T12 is 14.8 plus or minus 14.8 squared plus 58.92 over 2 times 4.91. So this is 14.8 plus or minus 16.67 over 2 times 491. So so the answer we need should be positive. So we only add. So we discard. In other words, we discard the minus solution. Okay. So we get 3.2 seconds. Is the time for the bike to travel all the way up and then -3 meters down. Okay. During that time, in the horizontal direction, meanwhile, we will have the distance in the horizontal direction is going to be equal to the initial velocity in the horizontal direction times t, which we just calculated, plus 1/2 times the acceleration in the horizontal direction times t squared. There is no acceleration in the horizontal direction, right? So the distance in the horizontal direction is going to be 31.72 times 3.2, which yields 101.65 meters, which is larger than 100 meters. Okay, so yes, it will make it. He will make it, or she. All right. Part C, explain how air resistance would affect the jump. Okay, so it's part C. Air resistance opposes with 2 S's, right? Opposes the motion. So the horizontal speed decreases. Okay. The horizontal deceleration reduces the range. Okay, so overall, the horizontal distance decreases, so the rider might not make it. Okay, might not make it. So this is, let me write it again. So the horizontal distance may decrease, in other words. Okay, this was question 18, guys. So we are ready to move on to question 19. Question 19, a pulley system is used to lift a 5,000 newtons load, or 5 kilonewtons. The system consists of one fixed pulley and one pulley that can move. Okay, so this is the moving pulley, I guess. Yes, okay. The pulleys are connected by a nylon rope as shown. Okay. The nylon rope will stretch. When it is used in this way, the weight of the pulleys and the rope can be ignored, and you may assume that there is no friction in the pulleys. The properties of the nylon rope, are Young modulus is 2.7 gigapascals, length before adding load is 6 meters, and the cross-sectional area is 3 times 10 to the negative 4 meters squared. Part A, the greater the length of a rope, the smaller the stiffness of the rope. Explain why. Okay, let's move to the back of the paper. So this problem A, so the stress is equal to the strain times the Young's modulus. Now the stress is force per cross-sectional area, and the strain is extension over the actual length, okay, times the Young's modulus, okay. So in other words, force is equal to area times delta x. Sorry, let's write it again. Area times the Young's modulus times delta x over x. Okay, so this is a constant which you can recognize as force is k times delta x. So that's the stiffness, guys. Okay, this is where earlier in the paper we actually used this formula. This is where it comes from. Okay, so k is the Young's modulus times the cross-sectional area over the unstretched length. So this is a constant. So as the length increases, the stiffness decreases. Okay, and that's the answer. And we can also work out the units. So the Young's modulus has units of pascals, so newtons over meter squared. And then the area has units of meter squared. And then the length has units of meters. So we uncover newtons per meters, which is the stiffness, okay? Which are the units for stiffness, excuse me. Okay, so this is part A. Part B, part 1. Show that the stiffness K of the nylon rope is about 1.4 times 10 to the 5 newtons per meter. Okay, let's do this. So B, part 1. So K is equal to the Young's modulus, so 2.7 times 10 to the 9, right, times the cross-sectional area, 3 times 10 to the negative 4, over 6 meters. And by the way, guys, I'm using this formula, okay? I'm just plugging in numbers. I didn't want to write things again. Okay, so 135,000 newtons per meter, which is 1.35 times 10 to the 5 newtons per meter, which is about 1.4 times 10 to the 5 newtons per meter, which is the answer, guys. Okay. Part 2. The pulley system lifts the 5,000 newtons weight at a steady rate. Determine the extension of the rope while the lift is taking place. Okay, part 2. We have that F is K times delta X. So delta X is F over K, but we have to also multiply by 1/2 because we have both parts contributing, right? So, or in other words, we can write, if we take this part of the equation, we can write that weight is 2 times K times delta X. Okay, so delta X is weight over 2K. Okay, so 5,000 newtons over 2 times 1.35 times 10 to the 5. So we get 0.018 meters, which is about 0.02 meters. Okay, so that's the answer. Let's move. Let's read the third part. Calculate the work done in stretching the rope. Okay, so part 3, the delta E elastic is going to be 1/2 times the force on a cable times delta X, but the force is 2,500 newtons, as we just said, because it is shared between the two cables, times the extension 0.02, so 25 joules is the energy. Okay, so this was problem 19, which marks the end of this paper. I hope these papers are useful. Let me know what you think about them in the comments. If you have suggestions, if you have anything to say, please say it. Please subscribe. Many people watch these videos without subscribing, so it would be cool if you subscribe. And see you in the next video, guys. Bye.